Virgo, Spica. Spica is on its way, mostly on the red giant branch. It is a B-class star, so it is a big one, very massive, very bright. It's a two-star system, though, and the two stars are so close together that they both are distorted. Their shapes are distorted. They've both been elongated in the direction of the other star. So those are the constellations and the stars and the deep sky objects. Again, you are responsible for understanding how these stars form in star formation complexes and how they end up being supernova remnants. And along the way, they're going to be red giants and they're going to be white dwarfs until they become either a type 2 or a type 1a supernova event. I think by now you might have a pretty good idea of the HR diagram. Remember, it is a plot of two stellar properties, temperature and absolute magnitude. You can either think of it as absolute magnitude or you can use luminosity. Temperature is what causes the classifications to be that way, O, B, A, F, G, K, M. Remember the main sequence, there's stars, pressure out, gravity in, stabilized. You get to the red giant stage, now you're fusing different atomic nuclei until you get to carbon. A little bit further up, you have moved off the main sequence. You've been fusing, and you can fuse all the way up to iron until bad things start to happen. If you are a very massive star moving horizontally across to the supergiant branch, again, lots of strange things can happen way up there in that part of the HR diagram that we not go into with this particular event. So remember, main sequence, red giant branch, supergiant branch, and the white dwarf branch, because white dwarfs, they're very, very hot, but they're very, very dim. They're hard to see, and they emit most of their radiation in X-ray. They will simply cool off, emit their radiation away over time, and eventually, trillions of years, they will simply cease to exist. Here is another HR diagram that lists some of the stars that are in this event to give you an idea of where they are. So here in the main sequence, you can see Regulus is there, Altair is there, Mizar, Vega is there, the Sun, Procyon. You can see that up on the very top we have Betelgeuse, and then underneath it we have Aldebaran, so you can see they're highly evolved, getting towards the end of their stellar journey. We see that Rigel is just off, a little ways off the main sequence. We see that Deneb is further evolved off the main sequence. Polaris is about three-fourths of the way across. There's Antares below Betelgeuse, and there's Procyon B, a white dwarf down on the white dwarf branch, along with Sirius B. These are spectra. Again, the way that the physical properties of these stars are determined is by analyzing the starlight which is called spectroscopy. These are the spectra for the Sun, G2, Arcturus, K1, and Procyon, F3. And you know now that Procyon is brighter, of course, then the Sun is in the middle, and then Arcturus is cooler, because Arcturus is actually a red giant and evolving on the red giant branch. So you don't see a lot of difference in the spectra between the Sun and Arcturus. They look pretty similar, but it's easier to tell the difference in the spectra if you compare Procyon to Arcturus. You can see there's much fewer absorption lines in Procyon than there is in Arcturus. And if you took, for instance, Procyon, if you took this entire spectrum, and this is only the optical part of the spectrum, only the visible part of the spectrum, if you took that, you printed it out on an 8.5 piece of paper, and you cut every one of those little strips out, and you taped them all together, you would have a spectra for the optical part of the spectrum only that would be 52 feet long. They take all of that and they condense it to, look at the lower left-hand side, the graphic, it says F5, and it gives one simple barcode that represents all F5 classification stars. So they take all of this information, they condense it into one little barcode that you see in your textbooks, and you will see that each one of those is unique to itself because that particular spectra is produced because of the temperature of the star. So every temperature of a star that gives it a classification of F5 will have that identical spectra, like a fingerprint. That's how you know by analyzing a star and determining its temperature from its spectra, you know what you have for a star. So spectroscopy is used to classify stars, and what is used are the hydrogen bomber lines are used to classify stars, and then temperature comes into play. But in order to determine what classification a star is, use the bomber lines, and then you use other lines because every single one of these stars has a unique set of spectra, which has a unique set of elements producing those emission lines. And it all comes down to this graphic here. Here are O through M classification stars. It shows their temperature from the O's, 30 to 60,000 K, down to the M's that are less than 3,500 K. And it shows you the strength of the bomber lines. They're very weak or non-existent for very hot stars. They're very weak and very non-existent for very cool stars. The reason being that in order to have a bomber line produced by hydrogen bomber line, you have to have electrons surrounding the hydrogen atom. You have to have an electron that jumps up into higher energy levels and then falls back down to the bomber line. That's the line that emits radiation in the visible part of the spectrum. So if you have a really hot star and all your electrons have been stripped away, it's too hot for them to maintain an orbit around the nucleus of the atom, they're all stripped away. So they can't obviously come back down to the bomber line and produce emission lines. And if you have a really cool star, they never get enough energy to leave ground state because the star is too cool to give them that much energy to transition up to a higher level and tumble back down. So bomber lines are very important in classifying stars, and along with those other unique elements. This lists some of them in the chart, other lines to look for. And for instance, in our sun, it also has a double calcium line that's unique to the sun. So here are some examples of different wavelengths. Again, I did not have to change this one from last year because none of these deep sky objects were taken out of the event for 2017. So we have Cas A and radio, infrared, optical, X-ray, and a composite of all of those. And we have the same thing for the Crab, and we have the same thing for the Orion Nebula. So remember you should go to APOD for every one of these objects, do a search for the object, and look at the list of images that come up, because any important image of any deep sky object is going to be an APOD astronomy picture of the day. So, and that will give you several different images to use to study with. So, and then of course, have an understanding of those different wavelengths where we have to go to observe those different wavelengths. We obviously have to put spacecraft in orbit around the Earth to detect X-rays because they don't get through. Gamma rays, this is all a good thing. Some ultraviolet radiation does not get through either. A lot of it, actually. That's another good thing. So we have to go above the atmosphere with spacecraft. Optical will get through with some distortion sometimes. Some radio gets through. The really longer wavelengths, though, of radio do not get through. So you have to see them from high up. That's why we have radio telescopes in places like the Andean Mountains in Chile. And, of course, there are many radio wavelengths that do get through, and we have ground-based telescopes also, like Socorro, New Mexico.